The examples. So what about one like this? Now, we were just talking about how to deal with the constant, right?
Yeah.
We got some options. We can group the 1/2 with the, like with the x to the 7th, and we can think of it as x to the 7th over 2 would be our u, and then our v would just be the radical. Or the other option is, and let's do this. The other option is we could take advantage of the property of derivatives, where if I differentiate a constant times a function, the constant just stays out in front of the derivative, right? So we'll just maybe separate that 1/2, and we'll just deal with the product in there, right? And then eventually we can just redistribute that 1/2 and we're all done. Okay, so if we differentiate then, what are we gonna get? We got our 1/2 out front. Leave that out there. What about the other part? What do I have to do to the radical? Okay, so it's going to be a square root is just a 1/2 power, right? So we could, if we wanted to, we could think about this function as being 1/2 x to the 7th times the quantity 8 minus x squared to the 1/2, right? Okay? And so we're suggesting that this could be our u, and that's our v, right? So let's do the product rule.
Yeah.
So what are we going to get? The product rule. X to the 7th times
1.
Okay, so I've got multiple layers, don't I? It's a chain rule issue. So the
Yes.
outside layer is hand to the 1/2.
Yes.
So the derivative of hand to the 1/2 is
1/2 hand to the negative 1/2.
okay. I got to go another layer with that. The derivative of what's inside then would just be negative 2x. Okay? Plus or minus, what do I do with the product rule? Plus. Now we flip it around, right? So I've got v times derivative of u would be
7x to the 6.
there we go. Okay? And so there's our derivative. Now we've just got to clean this thing up, right? So we could do a few things. We could cancel the 2 and the 1/2, right? So that's going to give us,
Negative.
there we go. So that's going to give us a negative x to what power total? You got an x times an x to the 7th would be
8.
x to the 8th times
We
an
also-
8 minus x squared to the minus 1/2.
You also have a 7x to the 6.
Okay, but now keep in mind, that's
Oh,
another,
yeah, okay.
right?
Yeah.
I've got another term there. Okay, so we got to clean up this term. We would just probably put the coefficient and the power out front, and we're going to get a 7x to the 6th times 8 minus x squared to the 1/2, right?
Yeah.
Okay, so now our goal is, we want to simplify this, but in the process of simplifying it, we'll be factoring, right?
Yes.
So we can factor stuff out. We can factor out the least powers of the like bases, right? So what are our bases here? X, because I've got x to a power, and my other base is
8 minus x squared.
good quantity 8 minus x squared. So let's take out. So what's the least power of x? And by the way, there is no common factor of the numbers, right? -1 and 7 we're stuck with. Okay.
X to the 6.
Okay, so we get out front, we get a negative 1/2 x to the 6th. And then what about my other base? Let's see. Yeah. So I've got those bases, right? Those are like bases. What's my least power of that base?
Negative 1/2.
Negative 1/2. So I get a quantity 8 minus x to the negative 1/2, and now we gotta see what's left over, okay? So we're gonna get a negative, what's this, what's gonna be left from my x's?
Squared.
X squared. What's gonna be left from my, nothing, right? Okay, that one goes away, everybody agree?
Mhm.
Okay, plus, how about over here?
Is that when it comes?
We're gonna get a 7, that guy completely is factored out, right? And then this one,
We did, did
Eight
X.
minus
8 minus x squared to the
one.
1, okay? Because, how come? Because we're factoring out an 8 minus x to the minus 1/2. And so the math we're doing there is we're just saying this, so I'll put this over on the side. 8 minus x squared to the 1/2 divided by my 8 minus x squared to the minus 1/2 is, so this whole thing is just that, isn't it? Right? Okay, it worked out so nicely this time, right? We got a 1 power. Is that just an accident? It won't be, but why, is my question. It's always gonna work out to be where if I've got some base in here, the base is gonna go away from, is gonna disappear completely, get factored out completely from one of the
Okay.
terms, and from the other term, it's gonna be to the first power. Now, in this case, this one, why did this one give us an x squared? Because as a product, as a part of our chain rule, we got an extra x in there, right? But that's the only reason, right? This more complicated base here, it's not an accident that it disappeared from the first term and it ended up being to the power 1 in the second term. How come?
Because if you take out the smallest, then you're always gonna get rid of one of them.
But how come it's always gonna be to the first power?
Well, because you subtract one from, when you take the derivative of the first part of the chain rule. And so then when you take it out again, you just add back.
Everybody get that? When you do the general power rule inside the process of the chain rule, which was right here, right? How did we get that negative 1/2? Because we subtracted 1 from 1/2. What's that make the difference in the exponents? 1, every time, right? So it's always gonna work that way, isn't it? Right? It's not just a fortuitous accident that we get it to work this time. I mean, it's always gonna be that way, okay? And so, what do we end up with then? So now we can clean this whole thing up, and we can write this as one big rational function. So what's getting banished to the bottom here? Well, we got a 2 that was on the bottom. We've got a negative exponent, right?
Yeah.
So that guy's going to the bottom. And if it's a negative 1/2 power, how could I write that
This
on
is
the bottom?
square root.
Square root. That's supposed to be x squared.
Yeah.
Okay, and the rest of the stuff is on top. So we're gonna get an x to the 6th, and then everything in here, we could simplify, right? We could distribute the 7 and combine like terms, and what are we gonna get? Negative x squared minus 7x squared is a negative 8x squared, and then I get a 56. And let's see, we could then, can we factor anything else out of the top? Out of there, take an 8 out, couldn't we?
Yeah.
Right, so there's one final step we could do. We could write this as x to the 6th, pull out an 8, and then we're left with 7 minus x squared. And on the bottom, we've got our 2 times the square root of 8 minus x squared. Okay, that's pretty useful, right? You know, once again, we haven't really used these things yet to do much, but if we needed to find the zeros of that derivative, pretty easy to do. We just find the zeros of the numerator, right? So one of them's gonna be at x equals 0, right? That's when x to the 6th is 0. what are the other zeros? X equals, when is, so go ahead, say it again. Plus or minus square root of 7, right? So those are our 3 zeros now, they're super easy to find. What are gonna be the places where the derivative is undefined, where the bottom is 0 but the top is not?
Plus or minus square.
Plus or minus the square root of 8, right? Get the idea? And we haven't really gone there yet, but that's where we're going next, right? Is using these things. Okay, let's try, how about that one? Quotient, oh, and then never mind, did we distribute the, I'm sure we did. Yeah, we get the 1/2, yeah, push that through, okay? What about here? What are our options here? Why don't everybody click these close? I think this is stuff, I know it's doing good stuff, but I feel like if you don't see this, you're not gonna get all this. So click all the Chromebooks close, please. What about this guy? What are our options? What's one option for doing this one?
Quotient.
We could do quotient rule, right? Because I've got a u over v, very obvious u over v. That works. Okay, what's another option?
We do the rewrite the.
Product rule. Do we lose anything by making this a product rule? No, not at all, right? Because we're using the chain rule anyway. When we differentiate v on the bottom here, it's already a chain rule, right? So why not, what do you prefer, product rule or chain rule? Or quotient rule? Product rule by a mile, right? Because it's, for many reasons, it may not seem that much easier, but one big thing is you got a plus between the two terms, and so you can't, it's hard to screw it up, right? With the quotient rule, it's easy to, there are many places where you can make a mistake on the quotient rule. So we would prefer to do this. Do you have to use, no, you can use the quotient rule, it's fine. What happens if you use the quotient rule? Well, you already get some stuff in the denominator that's just gonna end up there anyway, right? But the product rule would be easier here, wouldn't it? Right? So we just rewrite this as x cubed times the quantity x to the 7 minus 14 to what power? Negative 1/2. And then we're just doing the same thing, right? I mean, I don't know, do you guys wanna do that, or?
Yeah, let's do it.
Should we do that one? Okay. Let me just see, I can't remember what other examples I had. Okay. Okay, yeah, those are different. Okay, that's probably good to do. All right, so we got a product rule issue here. So then y prime equals, by the product rule,
X.
we're gonna get,
There.
so we got x cubed times,
1/2.
okay, good. So now we got a chain rule, outermost layer is power, right? Hand to the negative 1/2. So the derivative of hand to the negative 1/2 is
Negative 1/2.
negative 1/2
1/8.
hand to the, what power?
Negative 3/2.
Ah, negative 3/2, right?
Yes.
Negative 1/2 minus 1 would be negative 3/2, right?
Yes.
Okay. And then the next link in the chain,
We're gonna add
7x to the 6, okay. Good. And then we're gonna get plus, right?
Yes. Yeah.
3x.
All of that. Okay, so then we get, this guy is, now stays by itself, so that's good.
Yeah.
Okay. Times the derivative of u would be
3x.
Okay. Okay, so here's our, there's the important plus sign that splits the two terms. So now we're just gonna factor stuff out, right? We could, and let's go ahead and just factor things out while we're cleaning this up here. Well, no, let's not skip that stuff, that might be bad. So if we combine everything over here, what are we gonna get? What's our coefficient gonna be from this first term? Negative 7/2, okay? So, negative 7/2, and then,
X.
okay, x to the 6 times x cubed is gonna be an x to the 9th, right? Okay, times, okay, times, we get a x to the 7 minus 14 to the negative 3/2 plus, what's my coefficient here?
3x
Squared.
squared.
3, I'm gonna get an x squared right there. And then I'm gonna get x to the 7th minus 14 to the negative 1/2. Okay?
Yep.
All right. Okay, so now what here? We got a bunch of stuff. So what about the coefficients, the number constants? What should we probably factor out here? There's no common factor of 7 and 3, but yeah, we don't want to have a fraction in there, right? So let's factor out a 1/2.
Yeah.
If we factor out a 1/2, then what remains is going to be what's left, and we divide by 1/2, which is the same as multiplying by 2. Good. So we end up with, out front, we're starting off with a 1/2. And what's left, I may leave room for some other stuff out front too. So what's left from the numbers then? If I pull a 1/2 out front,
Negative 14.
I get a negative 7, right? Because I'm just multiplying negative 7/2 by 2, which is negative 7. Over here, I'm going to get a plus, good, so I'm going to get a 6, right? If I'm dividing 1/2 away from 3, I get a 6. Okay, what about, take out an x squared. So I've got two bases, one of my bases is an x. I can take out an x squared, leaving me with
X to the 7th.
x to the 7th, and then that's going to go away, right?
Yeah.
Okay, so how do I show you how to do this? Other base is an x to the 7th minus 14, right? Okay, so now what power am I factoring out?
Negative 3.
Negative 3/2. It's got to be the least power. Good, so we're going to take out to the negative 3/2, which means he's going away completely, right? So our first term is, all we're left with from the first term is just that stuff. What about over here? Well, I got my 3. What do I get if I factor my base to the negative 3/2 out of my base to the negative 1/2?
The base
To
is
the-
Base
to
of
the
1
1.
There you go. And remember, it's always going to be that way, isn't it? Right? It is negative 1/2 minus negative 3/2 is positive 1. So that's not so bad, is it? I mean, really, if you take advantage of that factoring process, it cleans up pretty nicely. And we end up then with, let's split it into the top and the bottom. What do we get on the bottom?
2.
So we got a 2, and then that's negative, right?
Yeah.
So we're going to get x to the 7th minus 14 to the positive 3/2 on the bottom. Okay, what are we getting on top then? I get an x squared, and then everything in here, we can simplify. If I distribute, I'm going to get a 6x to the 7th plus a negative x to the 7th,
So you get a negative x.
negative x to the 7th, and then I'm going to get a minus 84.
Yeah.
Okay? Okay, good. What could we, anything we could factor out of there?
Negative 1.
Maybe a negative 1 would be nice. So our very final answer then would be something like negative x squared times x to the 7th plus 84 divided by 2 times x to the 7th minus 14 to the 3/2. Once again, that's pretty useful. Yes?
Would it be beneficial at all to turn the denominator into a radical, or?
You can. You're free to do that. Not really. It's up to you. We recognize that means a radical.
Yeah.
Sometimes I think when you write them as radicals, it just looks complicated. Especially, if it's a square root, that's one thing, but if it's a rational exponent like that, you could write that as a square root cube, but doesn't that just look excessively complicated? It does to me. Either way is fine though. Yep. Okay, good.
Yeah.
All right, so how would we, you can decide if you want to do the whole thing, but how would we deal with this guy, you think? Couple ways we could do this. Whatever I should do.
The top and the bottom to the power of 1/2.
Okay, so we got some options here. We could make this into, there is a property of radicals we could apply here. You tell me, see if you can fill in the blanks from previous years. What is, if I have the square root of, could be any radical, the square root in this case, the square root of a over b could be rewritten as,
Square root of a over square root of b.
okay, so one thing we could do is we could write this then as a product rule, we could write this as 2x to the 1/2 times x plus 1 to the,
Negative 1/2.
okay, and that's fine. We could do this as a product rule like we've done. Okay? We could do this as a quotient rule. Now, if we're going to do this as a quotient rule, we could either split this up, or maybe even better than that, we could just do it as is, right? We could think of this as being the quantity 2x divided by x plus 1 to the 1/2. And then we would have, our first step would be a power, and our second step would be a quotient. Make sense?
Yeah.
Okay? How about if, we've already done a couple of them like this, but why don't we just do this one as a quotient problem? Okay, so there's how we're gonna start, that's why. So y prime then, so what's gonna be my first layer of my derivative? I got a hand to the 1/2, derivative of hand to the 1/2 is,
1/2 is negative.
okay, so we're gonna get a 1/2 times hand to the minus 1/2, and hand is 2x over x plus 1, right? Now we gotta go another link, now we gotta take the derivative of what's inside. What's the rule we're gonna follow there? Quotient rule. Okay, so we're gonna need some big brackets for the quotient rule, right? So quotient rule, what's quotient rule gonna give us?
Plus 1.
Okay. X plus 1 times 2 minus 2x times 1. Okay, divided by x plus 1. Okay? And then we're done, right? Because there's no other, I mean, we incorporated the chain rule, we took derivative of top and derivative of the bottom, we already used the chain rule in there, so we're done. We just gotta clean it up. Okay, now there is something we can do here. This is an important one too. It's a really good little trick. What can I do to that? It's 1 over the, so you get over that to the 1/2, right? But if I ever have a fraction to a negative exponent, what's the best way to deal with that? So just in general,
Multiply by the reciprocal.
yeah, just in general, if I have something like a over b to the negative m, what would I do? What's a negative exponent mean? Yeah, I'm splitting the fraction, right? So I could write that as b over a to the positive m, right?
Yeah.
Okay, so that's helpful here, because then look what we can do. We could write this as 1/2 times x plus 1 over 2x to the positive 1/2, okay? Times whatever I'm gonna get from all this stuff. Okay, well, let's simplify this. So on the top, if I distribute, I'm gonna get a 2x plus 2 minus 2x. That's just a 2, isn't it, right?
Yep.
So 2 divided by x plus 1 squared. Okay? What can I do? Anything, can I simplify? Cancel what?
And x plus 1.
True. What's the
Plus
first,
one.
what's the easiest one to cancel?
The
2.
Right?
Yeah.
Okay. And then, how about this? Now, look here, I've got an A, we already essentially did this one up somewhere, up here. But a radical is just a power, isn't it? A radical is a 1/2 power. So we could generalize this statement and say A over B to the M is really well. A to the M over B to the M, right?
Yeah.
Okay? And so look what I can do here with that then.
So then you can bracket.
X plus 1 to the 1/2 over 2x to the 1/2, right? Okay, that's helpful, because look what I've got here. 1 over x plus 1 squared. Right? So what's that give us? If I've got an x plus 1 to the 1/2 over an x plus 1 squared, right? I'm getting, I've got a 2x to the 1/2 on the bottom.
Yeah.
Yeah.
But what about all this stuff right here?
We have negative x plus 1 to that.
Okay, let's look at that now. So there's another property, and we're just going back to these, we're hammering these properties of exponents.
Yeah, you just.
So
subtract
a
x
to the
plus
m
1.
over a to the n, because I've got I'm dividing like bases, okay?
Is A to the N.
So what is that?
A to the
A
N minus N.
Okay, something I always do with my Algebra 2 classes is I write that another way too. 1 over a to the, what would happen if I kept the base on the bottom? Negative
N plus.
n minus m is what would it amount to? So here's a simple rule then, right? This is a great way to think about when you're dividing like bases. So how I always teach is I always say, okay, to simplify this, you're just going to keep the base where it has the biggest exponent and subtract the other one, right?
Yeah.
So in this case, 2 is bigger than 1/2, so we'll keep the base x plus 1 on the bottom and subtract the 1/2. So what do we get on the bottom?
3/2.
Now, is it that big a deal? No, we could have made it a negative 3/2 and push it to the bottom, but it does save a step.
Yeah.
Okay? So there's our answer, right?
Yeah.
Make sense? Okay, so shifting gears, what about something like this? Just not lose sight of, like, applying these things. So write the equation of the line tangent to the curve at x equals 1.
So you're gonna find y prime.
So we need, what are the ingredients we need to write the equation of a line?
Y for the slope
Slope and,
and the intercepts.
well, eventually, but really all we need, I mean, it'd be handy to have the intercept, but to write the equation of a line, I just need a slope and a, well, that's the slope, right?
Oh, yeah, I'm tired.
A point, yeah, right? If I have a point and a slope, I can always find the equation of the line. And I could get that by starting with 2 points to calculate. I mean, there's a lot of ways, but that's essentially the ingredients I need to write a line, is a point and a
Yes.
slope, right? Okay, so if I need a point and a slope, well, the point's pretty easy. We know the point we're gonna have, we already have the x coordinate. But we need the y coordinate. What do I do to find the y coordinate?
You put
Put
one.
one.
Put a 1, right? At x equals 1, y would equal 2 times e to the 1 minus 1 squared. So e to the 0, what's anything to the 0? 1, okay.
You just get 0.
So I get the point 1, 2, right? Now I just need the slope, right? Well, that's a derivative. So what's y prime going to be? Got 2 out front, just leave that there, right?
Yeah.
Okay, so now, what's the outermost layer of this? This is the one that we haven't, this is kind of one we haven't used in a little bit. E to the hand, right? What's the derivative of e to the hand? E to the hand, right? Okay. So I'm gonna get times e to the 1 minus x squared. Next layer in the derivative is gonna be
And,
what's inside the exponential function?
yeah.
Hand, right? So what's the derivative of 1 minus x squared?
Negative 2x.
Negative 2x. So we end up then with our derivative equaling, I could pull that out front and I get a negative 4x e to the 1 minus x squared. So now we can find the slope of the tangent line, right? So at x equals 1, y prime equals negative 4 times 1 times 1, right? E to the 0, which is -4. So that's the slope of our tangent line, and now we're good. Now it's piece of cake. Right now we get, we have a point, we have a slope, no big deal. Okay? Okay, last one. How about something like that? This is totally new. This doesn't really even generally show up in like a first year, or, well, yeah, first term calculus class, but I think it's worth seeing. This is what we call a system of parametric equations. This looks pretty familiar, right? We've got, what kind of? Look, we've got x defined in terms of t, and we've got y defined in terms of t, right? Okay, now let's just think for a second about what this is telling us, right? So this would be like, for example, a way that we could keep track of the position of an ant in the xy plane, okay? The ant's moving along the xy plane, and what's he doing? As time passes, what's his x coordinate doing? 'Cause that's really all this is. This is giving us his x coordinate in the xy plane, right? As t increases, it's just getting bigger, right? Makes sense? It's just a line with a slope of 1/pi and a y-intercept of 3. So from this perspective, or if we're looking straight down on this thing from above, right? So we're just only isolating the x motion of this thing. This is telling us what x is doing, right? Okay? What's his velocity in the x direction? So we could do something here. We could say, if we took a derivative of this, I could do dx dt, and what does that mean? Now this kind of goes to physics a little bit, right? Not physics. Yeah, so that the change in x over the change in time, that's telling us the rate of change of x. Well, isn't that just going to be the x component of his velocity? Everybody see that? So dx dt, we could even write that as something like v sub x. In physics, you guys have talked about components, right?
Yeah.
Vector components. There it is, right? That's pretty cool. So what is it? What's the derivative of x with respect to t? So I'm just differentiating that expression with respect to t. What's the derivative of 3? 0. What's the derivative of 1/pi times t? What's the derivative of t with respect to t? 1, right? So this is just giving us 1/pi. Right, so seen from above, what's this ant doing? Well, he's just moving along in the positive x direction at a rate of 1/pi. Okay, pretty boring, right? Okay, what about in the y direction, though? Let's look at the y direction. Well, this is telling us his y position as a function of time. What does that mean? Well, that would be like if I took this perspective over here where I'm looking straight at the ant from the distant x-axis. So all I'm really seeing is the ant moving up and down. I'm not really seeing the horizontal motion. Well, what's his position doing?
It's doing
Wiggling up and down, right?
Yeah.
So it's going to get up to a maximum of 1, y equals 1, and a minimum of -1, and just oscillate back and forth, right? So if we wanted to combine those two things, well, we can. What's the derivative of y with respect to t, which we could call v sub y? What's the derivative of sine t with respect to t? Cosine t. Aha. Okay, so and that makes sense, doesn't it? His speed, it's going to be doing this. It's going to be going up. From my perspective, it's going to be doing that. I can see it's going fastest maybe in the middle and slowest at the top and the bottom, which makes sense, doesn't it? Cosine is going to be a maximum at 0 and a minimum at pi halves and negative pi halves, right? Okay, so if we combine those two things, we would get a detailed picture of what this ant is doing. It'd be like combining the yellow movement is just going to be this. The yellow movement is just moving along in this direction. And the green movement is going to be, right? So what happens if I combine those things? I'm not going to get this exactly right, but you get the idea. It's just going to be right? Okay, what if we want wanna know what his actual velocity is. Or how about this, not velocity, I wanna know what the slope function is in the XY plane. So I wanna calculate what is dy dx. Can I apply the chain rule here? Look what I have dy dt and dx dt.
Yeah.
What did I do here? This is the version of the chain rule we almost never use. But let's review real quick. We've got, I'm saying, I've got u's and y's and x's, right? I can say something like this, dy dx equals dy du times du dx, right?
Yeah.
Okay, another way of saying that, by the way, I could write that as a quotient, and I could say dy du divided by dx du, right?
Yeah.
Okay, well, in this case, it's not a u, it's a t,
Uh-huh.
right?
Okay.
So couldn't I say then that dy dx here is equal to, whoops, dy dt times dt dx, or even better, dy dt divided by dx dt. Well, what is that? Dy dt is that. Dx dt is 1 over pi. So if I just flip and flip that fraction on the bottom and multiply, I get the answer. Dy dx equals pi cosine of t. Okay, that's pretty cool. That tells me I can pick a value of t, pick a frame in the movie, and the chain rule is telling me what's the slope here. In other words, in what direction is he traveling, right? Whatever the slope is, right? It's determining the direction he's traveling. Right? The slope of, like, if I go to this point right here, well, there's the slope, right? That slope is going to be given to me by, well, whatever value of t that is. That's going to tell me, I can plug that in, it's telling me the slope. Okay? Make sense?
No.
I mean, I wouldn't expect it to make total sense. I mean, I know we're kind of short on time. I just want to give you a brief introduction to a parametric system. A parametric system and how we can use the chain rule in a parametric system. This is, like I say, we're not really going to do stuff with parametric system. But if you're in physics, you can kind of see where this comes from, right? If I can break up the position into horizontal and vertical components, like if we're doing projectile motion or something, right? I guess I am kind of speaking more to the physics, people that are involved in physics here. This is going to make a little more sense, right? But you can see these are just the position components for projectile motion, right? For as an example, well, these correspond to the components of velocity for projectile motion. Look, they're written in terms of t's, right? Which is useful, because that's going to be, when we're doing kinematics, that's the common parameter, right? That defines the snapshot in the movie. Well, look what you can do with the chain rule. If we know, we can calculate things like, what is the, if we're looking at projectile motion, what is the direction of the cannonball at a certain time? Well, look, it's defined by the slope of that function, right? Chain rule gives it to us. Okay? Anyway. All right, I'm done.
Are we getting a new assignment?
Yes, you are.
Okay.